Now, I want to tell you about colour. But for me to tell you about colour, I need to start by talking a little bit about exactly what light is. Light is electromagnetic radiation. Light travels as changing, oscillating electric and magnetic fields. Now, we know this because of a fellow called Maxwell. Let me tell you a little bit about Maxwell. These four laws were already known. They're various laws involving vectors, involving vector fields in particular, the electric field and the magnetic field, and involving calculus. And Maxwell looked at these laws and he said, you know what? There are two solutions. One solution is nothing's happening. And the other solution is there's a wave travelling, a wave in the electromagnetic field travelling at the speed of light. Maybe, says Maxwell, maybe light is a wave in the electromagnetic field. Here's what he was talking about. Light travels as changes in the electric field corresponding with changes in the magnetic field. And the light travels with this wave. That's what Maxwell said as his description of light. And this turns out pretty much to be our current model of light. So light travels as a wave, basically, in the electric and magnetic fields. The wave motion is transverse as opposed to longitudinal. The field strength changes are transverse. The wave energy moves in a straight line. Now, we know this is true when it's travelling in a vacuum, or in fact in any uniform medium. We know that light bends, it refracts, when it changes from one medium to another. Actually, this still isn't quite the whole truth. Light travels in a straight line in the absence of gravity. When we talk about relativity, we'll talk a bit more about this, but actually gravity bends space in such a way that light no longer travels in straight lines. That's complicated. Leave it for the moment. Light is a wave in the electromagnetic field, and it travels at a very well-defined speed, the speed of light. Now, this number is basically 3 by 10 to the 8, and you've seen it before. 3.000 by 10 to the 8 is a perfectly good approximation for most of the times you're going to need it. This is the speed of light in a vacuum. We know already that light slows down when it goes into another medium. Now, think about that for a bit. If you've studied waves before, you know that this is the wave equation. If you haven't studied waves before, how much do I need to tell you right now? This is the speed of the wave. This is the frequency of the wave, the number of cycles per second. And this is the wavelength of the wave, the distance from one crest of the wave to the next crest. This relationship holds true for all waves, including light waves. Now, light, like any wave, comes in different forms based on the frequency and the wavelength. And remember that relationship. Let me write it for you in a colour you can see. V equals F lambda. All right? The speed of the wave is determined by the medium. Remember, refractive index. So if the frequency increases, the wavelength decreases, and vice versa. If the frequency decreases, the wavelength increases. So here is what we call a spectrum. At one end we have light waves, even though we can't see them, we only see the visible section. At this end we have electromagnetic waves that are high in frequency and low in wavelength, very short wavelength. At the other end we have waves that are low in frequency but very long. This is radio waves with 1 kilometre long waves. Now in the middle somewhere is the visible spectrum. This is the light that we can see, and it's only a very small band. And it goes from about 400 nanometres to about 700 nanometres. Think about that. Nanometres, these are hundreds of nanometres. These are about 10 to the minus 7 metres. Okay, 4 by 10 to the minus 7, 7 by 10 to the minus 7. They're very, very small wavelengths. The red end here of the visible spectrum has longer wavelengths, long relatively, and lower frequency. The blue end here has shorter wavelengths and higher frequency. Do I need to tell you anything else about it? Oh, yes. It is worth your while learning the order of colours in the visible spectrum: red, orange, yellow, green, blue, indigo, violet. To be honest, indigo is not really much of a separate colour. We call indigo separate because someone, I think it was probably Newton, decided that the spectrum had to have 7 colours in it. Red, orange, yellow, green, blue, indigo, violet. It's also worth your while learning the order of the overall spectrum, because it will help you to solve problems that start talking about radio waves or microwaves or gamma rays, and you to know something about, oh, this is at the red end with increased wavelength, this is at the blue end with increased frequency. So, to help you remember this, here are some mnemonics that you can use. Reading music is very unsatisfactory for xylophones and glockenspiels. That's from the right end of the previous spectrum. Radio, microwave, infrared, visible, ultraviolet, X-rays, gamma rays. Radio, microwave, infrared, visible, ultraviolet, X-rays, gamma rays. And here's a mnemonic to help you remember the colours. Now, some people just remember and learn it as Roy G. Biv. That was an interesting B. Let me fix that up and try again. Roy G. Biv. This is quite acceptable. Remember, red, orange, yellow, green, blue, indigo, violet. But if you prefer, reading over your geography book is valuable. If only I could have physics in here, it would be much more appropriate, but I need a word that starts with G. Okay, red, orange, yellow, green, blue, indigo, violet. Again, it's going to help you with problem solving. Now let me show you where all this is leading to. So, we know that if we send white light to a prism, we actually get coloured light coming out. And the reason is to do with what happens to the waves. When light goes through a prism, or when light goes through any other medium, the speed changes. But if you've studied waves, you know that the frequency does not change. And incidentally, the colour doesn't change either. The frequency corresponds to the colour. Now that has to do with the way the cells in our eyes actually detect colour. They depend on the frequency of that wave. But if the speed is changing and the frequency is not changing, then the wavelength must be changing. And if the speed is changing dependent on the colour, then it's refracting differently depending on the colour. So the refractive index depends on the wavelength, which depends on the colour. Different colours bend different amounts. And the wavelength changes when it slows down by a corresponding amount to how much the speed changes. That was a lot of complicated stuff. Let me go over that again. When light goes through another medium, its speed changes, but its frequency does not change. And that means its wavelength is changing. If the wavelengths are different, the speeds are going to change different amounts, and so the refractive index depends on the colour. And the wavelength is actually changing as it refracts. Notice when you look at this diagram that the blue light is bending more. We remember this as blue bends bigger. So you're going to come across problems that say, the light is hitting this side of the prism at the critical angle for yellow light. And you have to know, that's why you need the spectrum. You have to know that if that's the critical angle for yellow light, then yellow light's going along the prism edge, red and orange are not bending as much, blue and green are going to be totally internally reflecting because they're past the critical angle, because the critical angle, like everything else in refraction, is going to depend on the colour. I'll leave an example of that kind of problem for another video.